Good morning, ladies and gentlemen. Welcome to Yokogawa's Analytical Web Seminar, the pH measurement, basically the sodium reference versus a conventional reference. We'd like to thank you for taking the time to attend, and we hope you find the seminar helpful and informative. Before we begin, I'd like to go over some housekeeping issues. The audio part of the seminar can be accessed either through the teleconference number provided in the Info tab of your WebEx Manager window or through your PC speakers. To hear the audio through your PC, select the Communicate tab and join the audio broadcast. The seminar will last approximately 30 minutes, and then towards the end of the presentation, where time permitting, we'll have a question and answer section where I'll answer any questions that you guys may have today. If your question isn't answered directly, I will answer them directly to you via email or telephone. To submit your questions to me, either use the chat window or the Q&A section. Since I am manning the webinar today and computer by myself, I won't acknowledge anything in there to the end of the presentation. So for those of you that do not know me, I am Sherilyn Marlowe. I've been the liquid product specialist here at Yokogawa for about 5 years now. Prior to working for Yokogawa, I worked as a quality assurance technician for Bondo 3M, and previously to that, I worked for a nutraceutical manufacturing company called Deerland Enzymes. So let's go ahead and get started today. So, again, today our presentation is going to be the difference between a standard reference and what this new sodium reference or differential pH measurement reference is. Our goal for today's training is to examine how these two reference electrode types work and discuss the benefits and problems associated with each one. We will also talk about solutions for some of these problems for achieving and maintaining a stable and reliable reference signal for your pH loop. We hope to accomplish all of this while providing the information in such a way that even if you had a limited familiarity with pH applications, you will still gain some knowledge that will be useful to you. So basically, those of you that don't know, a conventional pH measurement is where pH is measured with a pH-sensitive electrode against a reference electrode with a stable and known electrode potential. However, differential pH measurement, or what our sodium reference is a pH is measured with a pH-sensitive electrode against a second ion-sensitive electrode. So to best understand the strengths and weaknesses of the two types of reference systems, we need to review the basics necessary for a pH measurement loop. To save time, we'll leave out the temperature electrode in our explanation. So for our purposes, to measure pH of an aqueous solution, the minimum electrodes that are needed are a measuring or glass electrode and a reference electrode. The measuring glass electrode measures the potential difference generated across the glass membrane. This voltage is then compared with the millivolt output of a reference sensor that is independent of the pH value of the sensor. Typically, this reference cell is a metal wire with an insoluble metal salt attached to it in a salt solution or gel electrolyte. This is separated from the process via junction. So the function of that glass or measuring electrode is to develop a millivolt potential that is directly related to the hydrogen ion concentration or the pH value of the solution being measured. This is done by comparing the process concentration to the concentration inside the electrode. The potential is measured in millivolts across this glass membrane that separates the two concentrations. The electrode typically has a glass body, and at the tip is a special formulation of a glass which is pH sensitive. Inside, we have a silver chloride wire immersed in an electrolyte. Both wetted surfaces, this inside and outside portion of the glass, form what is known as a hydrated gel layer, which is less than 40 nanometers thick. To function properly, this gel layer must remain wetted at all times. This is why the pH glass sensors are stored in wetted filled boots that have basically a buffer KCl solution in them. The internal solution of that glass electrode is usually 7 pH, so it's about 0 millivolts or neutral value. The difference of the potential between the internal buffer and the pH of the process is a millivolt value that indicates the true pH value of your process. For example, as the graph to the right shows, if the millivolt potential across the glass membrane of the electrode is positive 59.16 millivolts, then the process value will be a pH of 6. If the potential across that glass membrane is negative 59.16 millivolts, then the process will have a value of 8 pH. But this right here is only half the sensor. To obtain an accurate pH measurement, the voltage produced by the measuring electrode must be compared against a stable millivolt output from a reference electrode. Here we see the basic pH measurement circuit of a reference and measuring electrode. For the purpose of simplicity, again, we have excluded the temperature and the solution ground of the electrodes for the moment. Also shown are the voltage potentials that are present and which can adversely affect the accuracy of the measurement. If the measuring and reference electrodes accomplish their task correctly and all the potential negative effects have been taken care of that are indicated in the diagram by the various voltage potentials, the E2 through the E5, then the change in voltage we measure will be directly proportional to only the change of the hydrogen ion concentration or the pH of the process solution indicated by E1. Unfortunately, pH electrodes have a finite useful life, and as they age or are adversely affected by the process by coating, their reliability and accuracy will diminish, causing some of these voltage potentials shown here to be of interference, which means the pH measurement will also be affected. Conservatively speaking, about 80% of all pH problems are related to the reference electrode in one way or another. This brings us to our topic today. So let's take a closer look at the reference electrode, starting with standard conventional electrodes. So as we said, in order to measure the changing pH value of a process, we need a stable reference value to compare against. The scientist Hermann Nurse discovered that when a metal, the silver wire shown here, is combined with its insoluble metal salt, normally silver chloride pin, and immersed within a salt solution, normally the KCl electrolyte, which can either be gel form or liquid form, as long as that chloride potential concentration remained constant, then this combination of elements will always produce a constant millivolt potential. This constant millivolt potential is not affected by changes in the process as long as the silver-silver chloride element is not poisoned, the KCl solution is not depleted, or the liquid junction itself does not become coated or plugged. However, the reference electrode's second function is to provide continuity between itself and the pH measuring electrode via the junction. This means that the internal element is open to the process and can be affected by the process. The liquid junction does offer some protection to the reference electrode elements and the electrolyte. It helps to impede or slow down the ingress of the process so that the poisoning effects on that silver-silver chloride pin is diminished. But if the junction becomes plugged or coated by the process, the measurement will be adversely affected as well. Like we said, 80% of all typical problems of a pH measurement are caused by the diaphragm and the electrolyte of the reference electrode. And the main problems are the process can enter the electrode through the diaphragm, the junction, and poison that silver-silver chloride element, that the diaphragm junction is coated or become plugged, and basically by depletion of that internal KCl solution. If that's depleted, it will not, if any of these happen, that stable millivolt reading will not actually be fulfilled. To minimize the problems, design of the reference electrode over the years has been improved, and several different electrode design approaches exist today to address the various problems. So we've added multiple junctions, double and triple in some cases, to slow down the poisoning effects of the process on the silver-silver chloride element by putting additional barriers against the process. Also, the KCl that has been modified to help reduce its rate and depletion by thickening or making it a gel form. Different junction materials or configurations have been created, such as Teflon, ceramic, glass sleeve styles for helping with the plugging issues. And also, we've created a positive pressure or salt bridges, or what's known as flowing junction electrodes that are a great approach to some applications. This design basically forces a steady flow of that internal KCl solution in the reference electrode out through the junction because it's at a higher pressure than the process. Consequently, the process cannot enter through the junction as long as this higher pressure is maintained. By keeping the process out, that silver-silver chloride element is protected. So this design also helps to keep the junction itself clean and flowing, but obviously the KCl solution needs to be replenished, so there's still maintenance that is required with it. But for many harsh applications, the lifetime of these electrodes is poor and the customer is looking for a maintenance-free solution. So what's been developed now is what we call a differential that we'll talk about in just a minute. For those of you that don't know what a salt bridge type reference is, just to explain it a little more, it's a variation on the positive pressure approach. In this case, a standard reference electrode is placed in a chamber filled with KCl, and an empty dummy electrode is placed in the process. The empty electrode is connected to the chamber via tubing of some sort, and the process chamber itself is pressurized to a level that exceeds the process pressure. So the KCl is forced out of the chamber through the tubing and to the empty dummy electrode and into the process. So this still keeps KCl flowing out and does not allow the process to enter into the actual reference electrode. However, a thought to remember as we go along here is that a standard reference electrode, when all the problems are taken care of, does provide a stable reference that is truly independent of any changes to the process. So now let's just take a quick look at a different approach of the reference electrode. Remember, we still have to meet the criteria providing that stable reference value and provide the continuity to complete the measuring, continuity to the measuring electrode to complete the measuring circuit. So first of all, what's the difference between relative and differential pH? It is actually, differential pH is not an actual reference electrode, but a relative reference electrode. Let me explain what I mean. A conventional reference electrode supplies a constant voltage that acts as a reference line for comparing the output of the measuring electrode. With a fixed reference value, conventional pH is considered an absolute measurement. How does a differential measurement work, and how is it different? Like the conventional pH measurement, the pH glass sensor is still used for measuring the pH relative to this potential. But for generating a stable reference electrode, there are two common ways that this can be done, and this is where confusion comes in between what Yokogawa offers and what other manufacturers offers. You can either use a pH-sensitive electrode as a reference, which is installed in a buffer solution. The idea of using this glass sensor is that now the silver-silver chloride element of the reference is now protected against poisoning and other problems. The other way you can do it, which is the way Yokogawa does it, is that you can use an ion salt-sensitive electrode as a reference, and that's installed directly in the process. So a little bit more about this glass-on-glass method. This patented glass-on-glass differential technique is very similar to the operation of a combination electrode, with that it has two very important differences. One, the reference electrode is a measuring electrode immersed in a pH buffer solution, and second, the solution ground electrode is used to eliminate ground loops. The advantages of using a glass-on-glass differential method are that the reference electrode of the pH glass electrode installed in a buffer solution, which has to come in contact to the process via junction. This means the inner reference element is protected by the pH glass and cannot be poisoned, so it is a double junction salt bridge design type. And the system also includes a closed-coupled encapsulated preamplifier, so you can go further cable runs. Some setups are also available that allow the replacement of that buffer solution and the junction, so it allows for a little longer lifetime of the sensor and the analyzer. Okay, the way Yokogawa offers differential measurement is that we use a sodium ion or salt ion sensitive reference that is directly in the process. This is different from the glass-on-glass because when we use a sodium reference to measure, what we call is relative pH, not absolute pH. The sodium electrode is not an absolute measurement of pH because it is not an actual reference electrode, which supplies the constant reference voltage. For this sensor, the reference voltage of the sodium electrode is process determined or dependent on the amount of all salts within the solution. Point in fact, it's actually a measuring electrode which measures or responds to the concentrations of the salts in the process. Therefore, as the salt concentrations change, so will the reference voltage it generates. But when it's combined with a pH measuring electrode, we have what we call differential pH system. The system measures the concentration of the sodium or the salt in the process to determine the reference voltage. Thus, the live voltage of the sodium measurement makes the reference voltage process dependent versus being an absolute independent reference. So at first glance, it looks like the design of the sodium reference will solve the problems that plague the standard reference electrode. Because the sodium reference or salt reference has no junction, there's no path for the process to the internal element, so there's no poisoning that can occur. Since there's no junction, there's no plugging or coating problems to worry about, and there's no electrolyte depletion problem because there's no electrolyte. This means with the sodium reference, we have a perfect solution to our problems, right? Well, not quite, actually. There are some trade-offs to consider. Just like the variety of different standard reference electrode designs, some designs work better in certain applications, and no one solution solves every problem. While we have the sodium reference does overcome some of the problems we deal with by using a standard reference, it does have a few drawbacks to consider if we're to gain the best results when using this style of reference electrode. Some of the trade-offs are that it's not a true pH measurement, which we just discussed, and it is affected by sodium changes and the process, and it has a reduced measurement range. So by paying attention to the sodium concentration of the process in question and the measurement range required, we will have a choice between using a conventional or a differential pH loop. If we use the differential approach, then we have no poisoning of the silver-silver chloride element, plugging of the junction, or depletion of the internal KCl solution to contend with. So we will have reduced maintenance and improve our reliability. So the fact that we have to take in consideration the sodium concentration of the process, it sounds like a huge drawback, but for most applications, this is never an issue because there's more than a sufficient amount of sodium or salt to establish the stable reference voltage that we need. As a rule of thumb, we need to always remember that if the concentration of the sodium in the process changes by 25%, then there will actually be about a 0.2 pH change in the reference value. That's not a true pH change, but just because the sodium changed. Normally, sodium concentrations values that are above this 5 grams per liter mark are sufficient for a good zero, and you will not see changes as significant as 25% occurring. But processes that are below this 5 grams per liter mark, the sodium level is stable, then there should be no pH change. That's due to the reference, since it's not changing. But again, if the level changes by 25%, its resulting could be about 0.2 pH shift. But basically, just to get rid of this pH shift, all you have to do is calibrate it out by doing a 1-point sample count to the process. And in most pH control applications, this 25% isn't even noticed. But obviously, pure water applications are not acceptable applications for these electrodes since there's theoretically little to no salts present. So this graph here is just meant to show you that the solution with a 0 pH will change to show a pH change with the concentration level of that salt changing. Just to bring this, point again to everybody's attention so you clearly see why it's important to know. We have to know the concentration of the salt present in the solution before we consider this probe. So if you want to know what the actual pH shift is that you can expect to see for your process, it can actually be calculated. To do this, you have to know the concentration before and after the shift, as well as the chemical makeup of the process. So the millivolt change is calculated in the following equation shown here. You take basically the log of the concentration before minus the log of the concentration after, multiply this by the known 58 millivolts per step change, and this will give you the millivolt change due to simply a concentration shift. So just to show you a quick example, if you had a 0.2 weight percent sodium chloride solution and the process changed to 0.4, you wanted to know what the pH change would be. We already know what the concentration is after and before, and we know what the molecular weight of the process is. So now we just take the first information and fill in the blanks to the equation, and we calculate that the P&A of the solution before and after. So we see here that it's 1.48 before the shift, and it's 1.18 after the shift. Now we take that information and calculate what the resulting millivolt change should be. And in this particular example, it calculates out to be 18 millivolts, which is approximately 0.3 pH change. So we can do this for you. We just have to have this information up front to do it for you. So now let's take a look at what some of the differential sensors look like that we actually offer you guys. The first, and what's been around the longest, so some of you may already be familiar with it, is the pH-18 style differential sensor. It's a very unique design that does not resemble a typical electrode at all. It has a sodium-based ion-sensitive reference enamel and no-fill solutions for either electrode, because they're actually a pH-sensitive enamel on one end and a sodium-sensitive enamel on the other. So since there's no liquid fill and no glass, it doesn't have any of the problems that a conventional pH measuring electrode means. So this means that the slope is also fixed, and it doesn't require, because there's no glass, it doesn't require normal calibration. It's not a two-point calibration. It's a one single-point calibration that requires just basically adjustment of the sodium enamel to the sodium level that's in the process to establish that reference value. However, the pH-18 has two requirements for the use besides the sodium concentration. The second is that it has a pH range is only 3 to 11 pH. So if you're not within that range, it will not work, because above the 11 pH, the measuring enamel, the hydrogen ion enamel, is not linear, and below the 3 pH, the sodium enamel is not linear. Okay, the second design that we have to offer is it includes a conventional pH measuring glass electrode and a sodium glass electrode that's used as the reference. This measurement loop can be accomplished by either separate electrodes or this combination electrode shown here on the slide. Other than the obvious ruggedness the pH-18 type has, this design does have some advantages to consider. The measurement range is improved. It goes down to 2 pH, and it's less expensive, and it can be physically installed in a greater variety of ways. The combination version shown here is the model SC24V that has the unique design features that address some of the problems that we've been discussing. So this unique design incorporates basically all the measuring elements in a 12-millimeter body. It has the pH glass, the sodium reference glass, the temperature, the liquid earth that can also be used for ORP. The size and combination of elements allows us to more freedom and ways to be installed the electrode online. So here are just some of the quick specifications of this sensor. But what's important when using any differential measurement, you have to remember that you have to have a dual high impedance analyzer, because you're actually using two measuring electrodes. Each have high impedance, so where a conventional loop has a low impedance for the reference electrode and a high impedance for the measuring, this has two high impedance, so the instrument must be able to have two high impedance or the analyzer will not work. Okay, so let's now just quickly talk about calibration of the two differential types. For a conventional electrode, a two-point calibration is the best method for calibrating the pH electrode. The first point of the calibration corrects for the zero or the asymmetry offset of the reference electrode, and the second point corrects for the changing or aging of the glass measuring electrode. In order to achieve an accurate, reliable measurement, it's very important to calibrate for changes of both electrodes, and a two-point calibration is the best way to do it. However, now depending on which differential sensor you're using, depends on two different types of calibration. Let's first talk about calibration for the pH-18. As we mentioned earlier, the pH-18 design has no fill solutions of any kind, and since there's no fill solutions, the glass or measuring enamel does not age like a conventional pH glass electrode, so this means the slope is always fixed and doesn't require adjustment or calibration. So calibrating the pH-18 can be done by a simple single-point calibration that's just basically adjusting it to the sodium level of the process. However, for this 12-millimeter design, that have both a standard pH glass and a sodium reference, like the SC24V we just discussed, we need to correct for both the zero and the slope. However, standard buffers cannot be used. They can only be used for functional checks. You cannot use them for true calibration. This is because the sodium level in each of the standard conventional buffers are different. When using the SC24V, in order to properly calibrate for both the pH glass and sodium reference, we need to use buffers that are specifically designed with sodium-based references in them. So shown here are just some slides shown here on the slide is just examples of what's actually needed to perform the 2-point calibration. However, of course, once the sensor is online, it still may need to have a 1-point calibration to adjust the reference to the sodium level of the process. So let's take a quick minute and review what we discussed today, because we're getting close to our 30-minute mark here. But we reviewed the conventional pH reference electrodes are independent from the process effects that have problems with poisoning, plugging, electrolyte depletion, which adds to maintenance requirements. And finally, this type of pH loop requires a standard 2-point calibration for optimal accuracy. However, the sodium reference or differential sensor is dependent upon the sodium level of the process, and there are two different types which both have a reduced pH measurement range. However, they have no poisoning, no electrolyte depletion, and no junction problems, which requires less maintenance. And depending on the type of sensor, pH 18 or pH glass with a sodium reference, either a single point or a 2-point calibration is required. When it's a 2-point calibration is done, you need those special sodium buffers that must be used. And finally, we need to remember for either differential type of sensor, a transmitter with dual high impedance is needed to be used. So let's quickly talk about where we have seen differential benefit most frequently so far. Wet scrubbers are used as in utilities and paper mills and chemical plants to remove the sulfur dioxide and other pollutants from the gas streams. Undesirable pollutants are removed by contacting the gases with an aqueous solution or slurry containing an absorbent. The most common absorbents are the lime and limestone. In the limestone gypsum flue gas desulfurization systems, the consumption of the lime is controlled using pH analyzers, and it normally happens in two phases, absorption and then oxidation. After the fly ash removal, the flue gas is bubbled through the scrubber and the slurry is added from above. The lime or limestone reacts with that sulfur dioxide in the flue gas to create the insoluble calcium sulfite, as in the equation shown above here. The absorption rate is affected by pH, concentration, the temperature of the liquid, and the liquid-to-gas ratio. A pH sensor in normally the recirculating tank is used to control the feed of the solid lime or limestone. Neither lime nor limestone dissolves well in water, and therefore both are pumped in slurry form to the scrubber tower. And the lime slurry is more alkaline, having about a pH of 12.5, while the limestone slurry is more roughly neutral. So in a lime-based system, they would add lime when it drops below the 12, where limestone, they'd add it when it's around 6. So basically, the calcium sulfite will then either be further reacted with the oxygen to produce the gypsum. So here, the typical problems that they see is that basically the calcium compounds that are produced in the scrubbers tend to accumulate in the circulation loops and cause a buildup of scale. The lime can cause scaling in the pH electrode, which affects the measurement. And to ensure accurate measurement, frequent cleaning of the electrodes with acid was required, which adds both maintenance workload and cost. So having an accurate or reliable pH control is necessary not only to control the feed of the lime and limestone, but also to forestall the start of the scaling to make it much easier to prevent it, and it's easier to prevent it than it is to remove it once it happens. So since the SC24V was released in 2010, the U.S. has 4 site locations that have changed from either existing Yokogawa pH sensors or competitors' products, and currently we have 2 different plants in Europe that are using the SC24V in the same way. So basically, this is just a rundown of some before and afters. They were getting, competitors and ours were only getting anywhere from 3 to 6 months worth of life. Now they're getting anywhere from 9 to 18 months of life with one sensor. They were having to do daily cleanings with weekly calibrations and shift checks. But now, depending on where it is, They basically just do spot checks, and some plants have changed their procedures where they're only calibrating once every 6 months now. And again, they're spending less time and less money on acid to clean the sensors, so they're getting better control and they're getting better, they're trusting their pH readings more now. Unexpectedly, the pH-18 has been extremely popular within the pulp and paper industry, obviously because of its stainless steel rod design. The pH-18's ability to resist fouling and its structural strength lend itself to paper machines and pulp stock applications. We've seen pulp stock applications up to 12% have been successfully addressed with this pH sensor. This just shows you one of the test site locations that we've had, some of the variability that they saw in the pulp stock when using a standard reference electrode to after when they started using the pH-18. Again here, we're just showing you some of the success that they had in the accuracy of the measurement. After 3 months of testing, they wouldn't see grab samples, wouldn't change, but maybe 0.2 pH changes, and there was no drifting issues after a year, up to a year after the probe was put in. Okay, brine solutions are commonly found in electrolysis process or cheese manufacturing. This is actually what the SC24V, or the independent, when you break it into two, measuring and sodium reference, was designed to do. Traditional sensors have difficulty in this application because of inaccuracy and short sensor life, which is caused by the brine ions creating a large diffusion potential in the reference junction. The temperature of the chlorinated brine solutions is high, which increases this diffusion rate and therefore shortens the lifetime of the reference cells. And also the chlorinated brine is measured often close to the electrolysis cells so that its very high currents are present. So these currents will easily cause ground loop current problems, so that it will also, see shift changes or drifting issues, and it also shorten the life of the electrode. So evidently these problems are not related to the pH measuring cell, but most exclusively to the reference side. So therefore the solution of the problem must be sought in alternative ways of generating a reference voltage that is stable over time and that's independent on the pH value, thus resulting in the creation of the sodium reference element. So just to show you some more of the testing that the sodium reference, let's take a look at some graphical information. In this graph here, the millivolt output of both the pH glass and the sodium glass are measured against the calorimeter reference system. This graph is for 1 molar sodium chloride, so it's quite a strong solution. And the inner solution of the sodium glass is also 1 molar, so therefore the output is 0 millivolts since there's no difference. The line with the dots is the millivolt of the pH versus the common reference, and the line with the X's is the line for the sodium reference. The purple line is the difference between these two values and results in the millivolt output of the combination electrode. So what you see here is that at lower pH values, the sodium responds to pH changes, and therefore the purple line shows the loss of sensitivity at the low pH. So that's why it's not stable after 2 pH units. So it's, that's why you can't use it, because it actually detects caustic ingress of it. However, in concentrated brine solutions, the sodium concentration is much higher, and therefore the millivolt output of that sodium sensor is different than before. Here you actually see that it's 49 millivolts. Because of this, the sensor is linear, almost the complete pH range with only a slight loss of sensitivity below 1 pH. So basically, without going into too much detail, what these graphs are trying to show you is that the SC24V specs show the sensor's range is useful between 2 and 14 pH, but we're not saying that you can't measure below 2 pH. It depends on the actual sodium concentration. Because of the low limit of the sensor, it's actually based on what's in the process. The most important thing to understand with the sodium reference works well in salt solutions, because as long as the salt concentration is constant, the millivolt output of the reference cell is constant. This graph shows you here different salt solutions with reference potentials that are different, and always a process sample calibration is needed. Some other applications here, the pH-18 has the ability to handle steam cleaning way beyond the conventional electrode can experience. So steam cleaning actually improves the performance of the dual enamel electrode. This ability to handle the steam cleaning without killing the electrode makes it a natural selection in food and drug marketplace. Also, with proper CIP or caustic clean in places, that also doesn't affect the life expectancy of the PH18. So again, anywhere where they're doing CIP environments where normal electrodes would only last a few cycles, this lasts even longer. So thank you for your attention. That is the end of our presentation today. I'd just like to take a minute and answer any questions that people may have. So go ahead and answer them either in the chat window or the Q&A window, and I will answer them. Well, if there's no more questions, I just want to thank you guys for joining us today. And this is the end of the presentation, so you guys have our contact information here on the last slide. Please feel free to give us a call or email us anytime you have any questions. Thanks, and have a great day.